By the end of this video, you will understand what DSU is. We will look for the best possible implementation of a DSU. Also, we'll go through a standard problem. Let's first understand what DSU is. DSU stands for Disjoint Set Union, often called as union find, because of the two main operations that it provides. First is union, other one is find. Union A, B means merging of two set. Remember, DSU supports various set operations, among which two are union and find. Union A, B means merging of two set, a set that contains an element A and set that contains an element B. So imagine you have a set where you have various elements like A, D, E, and there is another set and there you have B, C, K. Merging of these two sets, which is a union A, B, will result in having a single set where you have all the elements. Union means merging of two sets that contains an element A and that contains an element B. Now there is another operation, that is find operation. Find A means finding the representative or the leader of a set that contains an element A. Again, let's take an example. Let's say you have a set where you have A, B, C and D, four elements inside a set. Only one of these four elements is going to be the leader and all the other are going to be the members. Find A means returning the leader of a set that contains an element A. Now the element A is in this particular set and leader of this set is D. So find A will return element D. Once these two definitions are clear, we need to look at the time complexity as well. Both of these two operations should take constant amount of time on an average. That means O of 1 time on an average. Once the requirements are clear, we will discuss DSU in following steps. First, we will build the logic. Then we will code that logic. We will try to optimize the code in terms of time complexity and space complexity. And then we will look for a standard problem. Okay, so let's get started. First, we are going to build the logic. Imagine each set as a tree. This is very crucial and important step. We need to imagine every single set as a tree, and the root of that tree will be the representative of the entire set. So when we are actually building the set, we will build in such a format that the root of the tree will always be the representative of this entire set. So don't worry about how we exactly got to this particular set that is represented as a tree. We will discuss that while we are discussing union. But the key concept that I want to highlight here is a parent array. See, in find operation, we need to return the representative or the leader of a set that contains an element A. So here, if I ask you, okay, what is find 4? The answer is very clear. It is 1. Why 1? Because find returns the leader of a set that contains an element 4. Now element 4 is present inside this particular set. And who is the reader? Root will always be the leader of this set. That means 4. Now if you look carefully, I need to maintain a link so that I can always traverse back to the root node, right? We need to maintain this ancestor chain, right? That's why we need this parent array. See, parent of 4 is 2. So I will go to 2. Parent of 2 is 1. So I will go to 1. Now parent of 1 is 1. That means we have reached the root node. There is no furthermore ancestor to 1. So we will just return 1. So no matter what they ask, whether they ask us find 2 or whether they ask us find 3, we will travel the ancestor chain and we can reach the root node. And remember, root is the leader of that particular set, right? And that's what find wants. So that's what we have coded here. See, if v is equal to parent of v, then we are just going to return v because v will be the root. If v is equal to parent of v, then v is going to be the root because there is no further ancestor to it. Otherwise, we will find the parent of v. So how it will look like for find 4? We will check if v is equal to parent of v. That means parent of 4 is 4? No, it's not. We'll call find parent of 4. Parent of 4 is 2. After that, we will check is parent of 2 is equal to 2? No. That means we again need to call find operation on parent of 2. Remember, parent of 2 is 1. So here it will be 1. Now, is parent of 1 is equal to 1? Yes. That means we have reached the root node. So we are going to return 1. Very clean and simple implementation. Very simple logic as well. We just need to travel the ancestor chain. If you have the clear idea about DFS, this is just a reverse of a DFS, right? In DFS, we start from root and we visit all the nodes, right? Here we are just traversing upward, visiting the ancestor chain. That's it. So nothing complicated here. So find operation is very simple. Now let's look at the union operation. In union operation, we will discuss how exactly we build this tree, right? So initially, let's say you have 5 different elements and all of them belong to different set. That's why parent of 1 is 1, parent of 2 is 2, and similarly parent of 3 is 3. All of them are actually in their own set. Let's assume that they are asking us to unite 1, 2, right? Let's solve this problem. Union 1, 2. So union 1, 2 means we are actually going to combine these two into a single set. As of now, they are residing in their own set. Our target is to combine them together. If you observe carefully, by combining what we mean, that we just need to create this particular link, right? And that is very simple to do. You just need to change the parent of 2 to 1. See, here we changed the parent of 2 to 1 and we managed to create this particular link. And if you look, now this has created a tree where 1 is the root node. That means 1 is going to be the leader where element 2 is present. Very simple and straightforward, right? We are just changing the parent. Let's again solve this problem. Union 2, 3. Let's say you have these 4 set 1, 2, 3 and 4 and they are asking us to unite 2, 3. How will you unite? Again, same thing, right? You are just going to change the parent of 3 to 2. That will create this particular link. Okay, it looks like our logic is working. Let's look for one more example. Let's say they are asking us to unite 2 and 4. Right? They are asking us to unite 2 and 4. So here is 2, here is 4. The logic that we build, what we will do, by the logic that we build, we just change the parent of 4 to 2, right? That will actually create this link. But when we change parent of 4 to 2, we actually lost this particular link. So if you observe carefully, ultimately what we have these 4 elements present in a single set, in a single tree, and 5 has been isolated completely. But that's not what we want in union. Union 4, 2 should have return us a set that contains all the 5 elements. Remember, union A, B means we are actually combining a set that contains an element A and set that contains element B. That means we are actually merging these two sets. But by just changing the parent, to 2, we created this link, but we lost this link. That resulted in a wrong answer. We ultimately created two sets, one set having 4 elements and another set having 1 element. 5 is isolated completely now. So this is not working, right? This is clearly not working. By just changing the parent, we are not able to solve the problem. If you observe carefully, here issue is not, creating this particular link. The issue is we are losing the information because we are, cutting off this particular link. We are actually changing the parent. Parent we are changing from 5 to 2. Parent of 4, earlier it was 5, now it is 2. So we actually lost this information. This is the main problem that we have here. So how are we exactly going to solve it? By changing the link, we actually lost the information. Why we lost the information? Because 4 wasn't the leader of this set. 4 was already pointing to somebody else and we cut that link and created a new one. So I just need to find an element that is not already pointing to any other element. So if you look into a tree that is not pointing to any other element, that is going to be the root node, right? So root node is not pointing to any other element. So rather than creating a link from 4 to 2, what I will do, I will create a link from 5 to 1. That means I am creating a link from leader of set B to leader of set A. So ultimately you will have something like this. So if you go back, here also, by our new logic, here also, we will not directly create this particular link from 3 to 2. What we will do, we will look for the parent of this particular set or a leader of this particular set, which is 3, and leader of this particular set, which is 1. So we'll create a link from 3 to 1. This is not right. We'll create a link from 3 to 1. So this is the final answer that we will have here. Parent of 3 will become 1. So if you look at the code, see what we are doing in union operation. First, we find the leader of set that contains an element A. Also we find a leader of a set that contains an element B. If both of them are different, both the leaders are different, then only we'll update the link. If both the leaders are same, that means A and B are actually residing in the same set, right? That's why they have the same leader. If they have the different leader, then we are actually creating a link from leader B to leader A. Like here, we created a link from leader B to leader A. So this is a simple implementation of a union algorithm. Okay, so once we have done the coding of union and find both the algorithms, what we will do, we will understand the time complexity of our current code. So let's look at the find operation. Here is a find code that we just built. If you look carefully, we are traversing node one by one in an ancestor chain. So let's say you have something like this. You have here 5, here you have 6, here you have 7, and till n minus 1 and then n. Let's say you have something like this, and if they ask you find n, what will you do? You will start from n, you will travel upward, right, one by one till you reach the root node. That's what we are doing in a find operation, right? And it's going to take n steps. So that's why the time complexity of find operation is O of n. Very simple and very clear proof, right? And if you look at the union operation, we are calling find operation twice. So if the find operation has O of n time complexity, the union operation will also have O of n time complexity, right? This is our current time complexity of our current implementation. But if you look at the requirement, it says that we need to have a constant time on an average for both of these two operations. So in this step, we are going to discuss the optimization on find and union. So let's start from find operation optimization, right? On the left hand side, you have a set which is represented in the form of tree, and you have the current implementation as well on the left hand side. Let's say they ask you find 7. So how will you compute find 7? Well, you need to start from node 7 and travel upwards till you reach the root node. That means you need to travel this entire ancestor chain. But once you travel this entire ancestor chain, you realize that you are not just computing the answer for find 7, you are also computing the answer for find 6. Because what will you do? If they ask you find 6, you will travel upward from 6, right? And what did you do when they ask you for find 7? You traveled upward from 7. So once you realize this, that you are not just computing the answer for find 7, you are also computing the answer for find 6, 3 and 2. A key observation here, none of the operations, that is find or the union, actually requires this entire ancestor chain. See, find only cares about the root of the tree, right? Only the root, the leader of the set. And union actually only cares that all the elements should present after union. You have, let's say, 3 elements here, A, B, C, and you have, let's say, 2 elements here, D and F. After union, all the 5 elements should be present in the resulting set, right? That's what union cares about. And find only cares about the root node. None of the operation actually cares about this entire ancestor chain. So let's look at the find 7 again. How will you solve find 7? You start from root node 7 and you travel upward. You go to 6, you go to 3. Remember, we are traveling upward by using parent array, right? Then we are going to root 2, then we are going to root 1. Again, now once we reach to the node 1, we see that parent of 1 is 1. Then we will return node 1 as the answer. So finally, find 7 will return 1. But if you look at this carefully, see, once this node 7 knows that root is 1. So what it will do? It will actually cancel out this particular link and it can create a direct link to root 1. That means parent of 7 will become 1 now, because we only care about who is the root. We don't actually care about this entire ancestor chain. We don't actually care about this entire chain. We only care about the root of the tree, right? Now, if they ask you find 7 again, you are not actually going to travel this entire ancestor chain, because 7 actually knows that the leader or the representative of this set or the root of this particular tree is 1. So it has updated the parent value of 7 directly to 1. So it will directly return 1 next time. It's not going to travel this entire ancestor chain. Likewise, while we are returning, 6 also knows that okay, 3 is not the root. 3 is not the root, 1 is actually the root. So it will cancel out this particular link and it will create a new link. That means parent of 6 will also be updated. Parent of 6 will now become 1. Similarly, parent of 3 will also become 1 and parent of 2 will also become 1. So now after doing all this operation, we ultimately have a tree like this. See, parent of 3 has become 1, parent of 7 has become 1, parent of 6 has become 1, parent of 2 has become 1. See, we did not lose any information. Find only cares about the root, and union only cares about all the elements should present in that particular tree or in that particular set. See, all the elements are actually present that were there before, right? All of them are actually present. Look, all of them are actually present here. And root for this tree and this tree is 1. So we haven't lost any information. So this is also called as path compression optimization. Why path compression optimization? Because see, we managed to reduce this entire ancestor chain to a single link, right? See, this is our old implementation and now this is our new implementation. So the only difference is here. We are updating the parent before we are returning. That's the only difference. So the time complexity of this particular logic is O of log n on an average. So we managed to reduce our time complexity from O of n to O of log n. How did we arrive at O of log n? By using path compression. There is a mathematical proof for it, why this algorithm actually reduces the complexity to log n. We are not going to deep dive it in this video. Now we will look at union operation optimization. To be precise, we will develop a technique to decide who will become the leader after combining the two sets. There are many possible ways, but most of them actually focus on reducing the height or the depth of the tree. Now let's look at our current implementation. What we are doing in our implementation, we are fetching the leader A, we are fetching the leader B, and we are just creating a link from leader B to leader A. Let's take an example. Let's say they ask you to do a union of 2, 1. So what will you do? You will create a link from 1 to 2. And then they ask you to do union of 3, 2. Then what you will do? You will create a link from 2 to 3. Similarly, if they ask you to do union of 4, 3, you will create a link from 3 to 4. And similarly, 4 to 5. So in the worst case scenario, the current algorithm will have a depth of n for n nodes, right? And this actually results O of n time complexity. That is why we need to reduce the depth of the tree. So our main objective here is to reduce the depth of the tree, right? That is actually causing the issue and creating a time complexity of On. Our current implementation doesn't take account for the depth. It actually randomly assigns the leader. It can potentially lead up to O of n time complexity. So how are we exactly going to reduce the depth of the tree? There are a lot of parameters that we can utilize, but here we will use size of a component, size of a tree to reduce the depth. Let's say you have two different sets, set A and there is a set B. Assume that size of set A is greater than size of set B. Then what we will do, while merging A and B, we will always create a link from B to A. So here we are actually attaching a smaller tree to a larger tree. So how exactly this will reduce the time complexity? Actually, this reduces our time complexity from O of n to O of log n. So this is the key observation here. When the depth of the tree is increased by 1, the size of the tree will at least double. Let's understand our key observation by taking an example. Let's say you have these 4 nodes and they ask you to unite 1 and 2. Right? How will you do it? Something like this, right? Now let's say they ask you to add 3 as well. Now if you look carefully, we are not directly going to add it here. We are going to merge this smaller one into the large one and we are attaching it to the leader. So it will happen something like this. So no matter how many elements they ask us to merge into this particular set, it will just keep on growing like this. See, depth of the tree is not increasing. But let's take one more example, right? Let's say first they ask you to merge 1 and 2. It will be something like this. Then they ask you to merge 3 and 4. It will be something like this. And now they are asking you to merge these two sets, right? Then what will happen? It will be something like this. 3 and 4. See, depth of the tree actually got increased here by 1, right? Component size has become double. So this is the key observation here. So that's what we have coded here. So first we are finding the leader A, then we are finding the leader B. We are checking leader A is not equal to leader B. Remember what we are doing? Whenever we are merging A and B, we are actually creating a link from set B to set A when the size of set B is less than size of set A. The small set will become a subtree of a large set. That's what we are doing here. If size of set A is less than size of set B, then we are actually swapping it. Then we are creating a link from small set to large one. This will actually reduce our time complexity from O of n to O of log n. If you combine both optimization, find optimization and union optimization, we will reach nearly a constant time query. It turns out that the final time complexity is O of alpha of n. Alpha of n is an inverse Achammer function which grows very slowly. Actually, this alpha of n, right? Alpha of n is 4 for n is equal to 10 to the power 100. So this grows very slowly. Just to have a simple mathematics here, according to our key observation, size will always be greater than or equal to 2 to the power depth. Why? Because one increment in depth must result in doubling of the size. This we just observed from our previous example, right? If we apply log on both the side, this actually reduces the time complexity from O of n to O of log n. Let's go through the problem. Given a weighted undirected graph, we want to find a subtree of this graph that actually connects all the vertices. It has the least weight. That means the sum of the weights of all the edges is minimum. Every single edge has a weight. We need to select edge so that all the elements, all the nodes are connected, but the sum of the weights of all the edges that we select should be minimum. As we are finding the minimum weight, it is called as minimum spanning tree problem. So see, this is the undirected graph that is given to us and we need to select the edges. So if you look carefully, if we select these 3 edges, we will get this particular tree and all the elements are connected here and the weight is the least weight, right? So answer for this will be 14, right? So how did we arrive to this particular tree? So let's take all the edges and sort them in ascending order. After sorting, we will take edges one by one. We sorted on the weight, right? So here weight is 3, here 4, here 7, here 8 and 9. So we'll take this particular edge first. Then we'll check whether A and B are actually in the same set or not. If they are not in the same set, then we need to merge them, right? Merge them together. For that, we are actually going to use this particular edge only. Why this particular edge? Because all the edges that we are going to encounter later on will have more weight than this, will have more cost than this. Remember, we sorted based on the cost or the weight of the edges. So we have to take this. So what did we do? We first checked whether A and B are residing in the same set or not. If they are not residing in the same set, we are actually going to unite them by taking this particular edge. And that's how we will get this particular tree. Try to code this. It's very simple. We will take a look at it later on as well. Remember, we are not here to master DSU. DSU is just a tool for us to develop problem solving skill, and that's what we are trying to master here. We will look at more and more tools. We will try to utilize those tools in various different problems that will actually develop our mindset to solve various problems based on the information that we have. We are here to master the problem solving skill. I hope that is clear.